Okay, so last time we were talking about dot products. Very, very briefly, I mentioned that there was this thing called a dot product, and it's kind of a multiplication for vectors. Again, you know, we have this new object that we're talking about called vectors, and we talked about last time what it would mean to add them, and so pretty reasonable question, what would it mean to multiply them? And we come back to this question that we had before, which is, well, what should it mean, right? We don't want to just write down a formula arbitrarily. We want to have a formula that is geometrically natural in some way. So some application, some use that we're going to make of vectors, something that is relevant to vectors, we want the formula that we come up with to fit in with that. So now what I'm going to do here is a little bit different from what we do with vector addition. With vector addition, we came up with the application, the interpretation first, right? Namely, we decided we want vector addition to relate to concatenating displacements. Okay? That's not what's going to happen here. What's going to happen here is I'm going to write down a formula. Sadly, it's hard to come up with what the geometric interpretation of this formula is without having the formula first. So it is a little cart before the horse in some sense, but that's just kind of the way it works out. So here's the formula. If you have two vectors in R3, then this is the formula for what we call the dot product of those two vectors. Now let me zoom in on that actually. Quick moment. You'll notice that in this formula there is a dot in between the two vectors. Now, y'all have seen various different notations in the past for when you multiply two numbers, right? If you have, you know, A times B, you might put A dot B, or you might put A and then, you know, in elementary school you put a little times, a little cross symbol, right, and then B. Or once you get to algebra, you start to realize you could just write AB, and that having them next to each other sort of implies that you're multiplying them. So, okay, that's all fine, but for vector multiplication, you do not have any such flexibility. If you're going to write down the dot product, you have to put that dot in there. And part of the reason why is there are two different kinds of matrix multiplications we're going to talk about. So if you don't put anything, it's not clear which matrix multiplication you're talking about, right? And if you put the other symbol, then of course it's very confusing. So you have to put the dot. Be sure to do that. So the formula is a little bit of a weird formula, to be fair. Here's the first weird thing about it. A vector dot product with another vector is not a vector. Vector dot another vector is a number. It's a scalar. Right? That seems a little bit weird, and I guess it is, but this is, believe it or not, going to end up being pretty geometrically natural. We'll see that over the next few minutes. But do keep in mind that a vector dot a vector is a scalar. Okay. Second thing that's a little weird about this is it almost looks a little contrived, and if you look at the formula here, we're multiplying the corresponding coordinates, and then, I don't know, it seems a little too easy, and then arbitrarily, seemingly, we're adding it up. And the argument could be made that this formula appears to be a little too simple to possibly be useful, right? How is this going to be geometrically natural? And it's very surprising how it turns out to be, but I don't know, you should be a little skeptical perhaps at this point. So let me first observe a few algebraic properties. These are pretty boring. I'm going to write them down anyway. Again, you know, even though this formula looks very familiar, so familiar as to be boring, right? This is a new operation that we've just defined. When you write down a new operation, you can't just assume that it behaves like its sort of elementary school counterparts. And we're going to see a little bit later today, in fact, an operation that, in fact, does not have properties of this sort of, you know, expected sort. So it's very worth observing. The dot product is commutative and distributive, and what you might call here scalar associative. All righty. So now let me observe with this formula, which gives us these properties, question, are we impressed yet? Does this seem like a valuable operation? Is this something that we can do something with? And I hope right now that you're unimpressed, because right as of the moment, I've given you zero connection to anything geometric, anything physical, right? I wrote down a formula, and this formula relates to itself in ways that are, I guess, natural, but so what? Where's the foot in the door? How do I relate this to the real world? I haven't given you any such thing yet. So I'm going to give you a few such things. The first one I write down just because it's easy. We also are going to use this quite a bit, but this alone is really not the reason why we like the dot product. Nevertheless, cool fact, if you take a vector, dot it with itself, you get the square of the magnitude of that vector. Now, it's easy to prove, right? You take a vector and dot it with itself, you can see right there you're going to get the sum of the squares of the coordinates. And we saw last time that that's is the square of the magnitude. The magnitude is the square root of that expression. Okay, so it's an easy proof, not hard to see. Nevertheless, this is a connection between our dot product that we just defined and something that's geometrically natural. This is kind of our first little foot in the door. So this is the first, hey, maybe this is useful after all. Okay. All right. That's not really enough to justify the operation. One of the really big ones here is what we call the Cauchy-Schwarz inequality. And that's this right here. And this is starting to get more impressive. Look at what the Cauchy-Schwarz inequality says. Let me zoom in on that. Any two vectors, for one thing, not just a vector with itself, right? Any two vectors, you dot product any two vectors, you think it also about the magnitudes of those two vectors, and there's a pretty significant little relationship here between that dot product and those magnitudes, in that not only is the dot product less than this product, but the absolute value of the dot product is less than that product of magnitudes. So this is useful sometimes. It's not as strong as another fact that I'm going to show you in a few seconds, at least in terms of how it gets applied in Math 212. However, this fact shows up in many other applications, in many other situations, in a more general form. Those of you who will take Math 216 with me, or at any point, we'll see kind of a generalization of the idea of a dot product. There's a more general form that's used in a surprisingly large number of different subjects, called an inner product. There are many different inner products that are used, again, in different ways. And all inner products, appropriately interpreted, which again, Math 216, appropriately interpreted, the Cauchy-Schwarz inequality applies to all inner products. So in some sense, what we're seeing here is just the tip of the iceberg. It's a special case of the general Cauchy-Schwarz inequality. That being said, this specific one is not as strong as this next fact I want to show you. Here. Okay. So this next fact says that if you look at a dot product of two vectors, so there's your two vectors, you take the dot product, it equals this expression, and that expression is made up of three all geometrically natural objects. So this is a really surprising fact. So length, very geometrically natural. Length, again, very geometrically natural. And angle, which is extremely geometrically natural. So it's a weird fact. One of the things that's always blown my mind about this is that this formula here is defined with four-function arithmetic, right? It's just addition and scalar, well, we're just looking at coordinates, and it's just addition and multiplication. Two-function arithmetic, in fact. Right? And yet, this expression that it's equal to involves square roots and cosines. seems a little counterintuitive, right? How could something that involves square roots and cosines always be computed with two-function arithmetic? So very counterintuitive. Also, and I've made this observation before, but that is defined purely algebraically. Just an algebraic formula we wrote down, whereas this is purely geometric. Right? And so that's pretty surprising when you have such a big non-intuitive connection. Something that's way algebraic connects to something that's way geometric. It's a little surprising. So it's a wonderful formula. We're going to do a lot of stuff with this formula as we go through the course. So here's our picture. Oops. The picture in question, we have these two vectors. The angle theta between them is the theta in the formula we just talked about. And the way that we're going to prove this formula, pretty straightforward proof. We start by looking at that vector, v minus w. Okay. And this is a kind of a weird little strategy we're going to take in this proof. The first thing we're going to do is write down the magnitude of that vector. We're going to write it down with the law of cosines. And this is a flashback to a long time ago when y'all were in trig class, but I hope y'all might remember that when you have a triangle, not necessarily a right triangle. So instead of that being a right angle, thus making this a hypotenuse, if it's not a right angle, then you get something that looks kind of like a Pythagorean identity, but because that's not a right angle and that's not a hypotenuse, you get a correction term that looks like this. So vague memories, perhaps, trig class 2-3 years ago. If you haven't seen the law of cosines, I encourage you to Google it or find your old trig textbook. I don't know if y'all still have your old trig textbook, but Googling it should be sufficient. And see the law of cosines. It's a really useful fact. It comes up in a variety of different little instances, such as this one. So law of cosines tells us this. Now, it tells us length squared of v minus w. So what? Well, the thing is, length squared of v minus w I can compute in a different way. I can compute length squared of v minus w by doing a dot product of v minus w with itself. Remember, that was the first property that we established for dot products, is that any vector, dot product with itself, gives you length squared of that vector. And then I can kind of take this this expression here and FOIL it out, which is what I've done there, and sort of expand, write down all the terms, and you get this. So what we have here then is two formulas, both of which compute the same thing, length squared of v minus w. And therefore these two resulting equations, these two things that length squared is equal to, must be equal to each other. So looking at these two things that are equal to each other, you'll notice you can cancel the v squared, you can cancel the length of w squared, you can cancel the factor of minus 2 that is in both of the remaining expressions, and then all you're left with is, I'm running out of colors here, that equals that. All right, see how it works? Everybody happy? It's a very tricky little proof. This is what I like to call a mathematical bank shot, because we get to where we want to go by starting off in a totally different direction. Namely, we started by studying this expression we're not interested in, length squared of v minus w. And yet that got us to what we wanted. Okay, so that's the big formula for dot products. Now, again, we talked about the Cauchy-Schwarz inequality. I claim, and I'm going to leave this as an exercise for you guys, I strongly encourage you to give this a shot. I claim the Cauchy-Schwarz inequality immediately follows from what we just proved. Namely, if you know this, which we do because we just proved this formula, you can use that alone to prove the Cauchy-Schwarz inequality. And roughly speaking, how you're going to do that, and again, give this a try on your own, just take this equation, take the absolute value of both sides. Absolute value of v dot w left side of the Cauchy-Schwarz inequality. And then you just have to ask yourself, what can I conclude about the absolute value of this product? And of course, we have a couple of lengths. Lengths are positive, so they are their own absolute values. And then what do you know about absolute value of cosine? And that allows you to deduce Cauchy-Schwarz. So again, I'll let you fill in the blanks on that, but please do give that a shot. Okay. Here's a variant of the formula we just proved. If you solve for theta in the equation that we just wrote down, there you go. And this tells you that if you have two vectors and you want to know what the angle between those two vectors is, plug into this formula. And conveniently, all of the stuff in here is easy to compute. Computing a dot product, if you know the components of both your vectors, that's two-function arithmetic. It's really easy, right? If you again, if you know the components, these two magnitudes, not that bad. Okay, there's a square root in it, but yeah, whatever. Yes.
Sorry,
yeah.
As a question that the question involved the cosine. You
Yeah.
have to worry about the fact that the location of the angle could change it to sine, or is it always cosine?
Always cosine. It's always cosine. Yeah, exactly. And that cosine came up again because of the law of cosines, right? And so yeah, it's always cosine. Yep. Yep. Sure. Anybody else? Okay, so yeah, so we have here a handy-dandy tool for computing the angle between two vectors. And side note, without the dot product, that would have been a pretty hard question, right? If you have two vectors in the plane, okay, not that bad. Maybe this angle plus that angle, and you can probably kind of piece it together. But if the angle is like between vectors, like you have one vector that's pointing kind of down that way and another one that's pointing up that way, it's not, you can't just do this angle plus that angle, because that's not how angles add, right? You're measuring an angle on a kind of a sloped plane. It's really not clear at all how you'd go about doing that. And yet, dot product does it for us in a snap. So very cool fact. Here's a quick example. A couple of vectors. Let's compute the angle between these two vectors. Notice all I do is I compute the dot product and the magnitudes, and I take those two numbers, those three numbers, and I plug them in, into the formula that we just proved. The formula there. And that gives us our answer. I'm going to leave this answer in this form, by the way. That's an exact answer. I could plug that into a calculator or computer, I suppose, and get a decimal approximation. But the good thing about decimal approximations is that they're numerically sort of relatable. You can get an idea of approximately what it is. You can pull out a protractor and kind of see that angle. But the bad thing about it is it's an approximation, right? So in a math class, we're going to be interested in exact answers. There are a very few instances where you're going to plug into a calculator so we can see what this number approximately is. But most of the time, what we're going to be interested in is exact answers. An arc cosine of 4 over 21, it's an exact number. Okay, so a few applications now. If you have a couple of non-zero vectors, those vectors are perpendicular if and only if the dot product is 0. Again, geometric fact, algebraic fact. So an interesting connection between two seemingly different things. The geometric notion of perpendicularity, the algebraic notion of a certain algebraic formula of equaling 0. Now, this follows immediately, of course, from the equation that we just proved, right? You look at this fact here, and if the vectors are non-zero vectors, then these are not 0, and therefore this is 0, namely theta is pi over 2, if and only if that's 0. Dot product equals 0, right? So easy proof. Perpendicular means dot product is 0, dot product is 0 means perpendicular. Again, that makes the assumption that these lengths are both non-zero. If the length is 0, that kind of throws a wrench into our, in fact, even worse than the algebraic wrench it would throw into our argument, it throws a wrench into the idea of what does perpendicular even mean. You know, if you have this vector like that, and then the 0 vector, well, it doesn't have a direction. So can it be perpendicular to, it just doesn't make any sense, right? So the whole thing kind of goes useless. So we make a new definition. We define two vectors to be orthogonal if either of these things happens, either perpendicular or one of the vectors is the 0 vector. And then you get a really nice simplification of the above corollary, and that is V and W are orthogonal if and only if the dot product is 0. In some sense, you could say that the definition of orthogonal, two vectors are orthogonal if and only if dot product is 0. So this encapsulates several possibilities. One possibility is that the vectors are non-zero and perpendicular. Another possibility is that one of the vectors is 0, or both of the vectors are 0. Right? And it's surprisingly relevant. Two vectors being perpendicular versus one of the vectors being the 0 vector, surprisingly often you want to pair those together. So orthogonality is a very useful idea. Usually, in fact, orthogonality is more useful than perpendicularity. All right, so quick application. Here's a couple of vectors. Let's decide if they're perpendicular. Well, they're obviously non-zero. So asking if they're perpendicular, effectively I'm asking if they're orthogonal. Right? And so take the dot product, see what you get. Dot product ends up being 0. So yes, perpendicular. I don't have to draw a picture of them. I don't have to try to figure out how to get my hands on the angle. Dot product is 0, done. All right. Okay, so let's, here's another application. I want to talk about components. Here's a picture of what components look like. If you have a vector and a second vector. Now my second vector here, I'm going to, that W vector, I want to think about the line through the origin that second vector W defines. When I ask what is the W component of V, what I'm asking is this vector V, it points, some amount in some direction, but to what extent does that vector point in this direction? In other words, I just want to sort of drop a perpendicular to that line, and I want to know how far does V point in that W direction. Does everybody see what the sort of the picture is here? Okay. So how would I go about computing this? Well, it turns out the dot product is a wonderfully convenient tool for this. Here's the algebra up here. We'll start with this. Just looking at the triangle here, let's look at this blue triangle. This component, the component that I'm interested in, and the magnitude of the vector are two sides of a right triangle. They're related by the by trig function on that angle. Think, flash back to your high school trig class. Think about, how this angle relates to that length, and I think you can persuade yourself without too much trouble that the cosine of the angle is the component divided by that magnitude, and so the component is this little product. Okay, now that's a trig concept, so stare at that, make sure you're comfortable with it, take the time. If you need to refresh your trig, now would be a great time to do that, but that's where that goes. So writing that down, so what we wrote down up there was that the component is this times this. Now I am going to multiply and divide by the magnitude of W. That's perfectly free, right? Algebraically, multiply and divide by the same thing. Nothing happened. So we do that, and what we note is then that the numerator becomes exactly the dot product that we just got through talking about. Yeah, it's a wonderful little sort of lucky coincidence. That being said, you then have a convenient formula for how to compute components. If you want to compute the component, to what extent does this one vector point in the direction of this other vector? There you go. Dot product divided by the magnitude of the direction vector W. Okay. This gets rewritten sometimes as a means of interpreting the dot product. It's symmetric, of course, so you can do it either way. One of the unsatisfying things about dot products is students are constantly wanting to know, well, yeah, but what is the dot product? I know we have a formula for it. Yes, it relates to certain geometric objects, but point to it. Where is it? Right? I want to see a picture of the dot product, and I can't give you one in general. So it's very unsatisfying. When we add two vectors, I can point to the sum. You got that vector and that vector, then there's the sum. There, I've got a picture of it. I can point to it. It's visible. The dot product, not so much. So this is a kind of a consolation prize, sort of a little picture of what the dot product is. So the dot product of these two vectors is the magnitude of V times the component in the W direction. So it's the product of those two lengths. So one way of interpreting this is that it's kind of a combined extent to which these two vectors point in the same direction. So it's very loose and sloppy, and I can't point and say there it is exactly, but that's sort of one way you can think about it. Here's a better way, really, and that is to think about a special case. In the special case where one of the vectors is a unit vector, the formula really does become a lot simpler. If, for example, let's look at this equation here and consider what happens if W is a unit vector. Well, if W is a unit vector, then that's 1. And then the equation becomes that the dot product is simply the component. All right, now, so the good thing about that is it rolls off the tongue nicely. The dot product is the component. The bad news is it's only true in the special case. So, anyway. All right, here's another application. It's an old physics idea. How many of y'all have had a high school physics class and remember that there is this idea called work? Show of hands. Okay, good, most of you. If you haven't, don't worry about it. All you need to know about work is that it's a way of trying to get to quantify how much energy it takes to accomplish a certain task. Right? So, for example, let's take this remote control. Suppose I want to lift that remote control up to where my hand is up here. It's going to take a certain amount of energy to do this. Down here, it's kind of heavy. I've got to pick it up all the way. A certain amount of effort that goes into the task. So the way we define work in a high school class is we take the weight of the object. So how much force do I have to exert in the process of lifting it? And then I multiply by the distance that I have to lift it. So the idea is that heavier things, yeah, it takes more work to move them. Right? If I have to move it a greater distance, if I'm carrying all of my stuff up 4 flights of stairs to a new dorm room that you guys might have done recently, right? That's more work than if you're climbing up to the 2nd floor. So it's a pretty physically relatable formula, I think. Work equals force times distance. Okay, now, so that's all you need to know about work coming into the course. Now I want to give you a multivariable point of view, a little bit more sophisticated point of view on this, and that is we have to acknowledge that what I just told you is an oversimplification. Work is not always force times distance because, for example, the remote control, if I say, yeah, 3 feet, well, vertically, that's a certain amount of work, but horizontally, not so much. So it's not just distance that matters. It's to what extent is the distance that I'm moving it in the same direction as the force that I am applying. So as I'm holding this, however I might be moving it, the force is always up. I'm exerting force up because gravity's pulling it down. Right? So that the relationship between the direction of the force and the direction of the displacement, whichever way I might be happening to go, matters. So the way I'm going to write that down here then is to talk about how the force that I'm interested in is really a component. I don't really care about how much the thing weighs. I just care about to what extent are you pushing in the direction that you're going. Right? So, and conveniently, we have a formula for components. Components are computed like so: dot product divided by the magnitude of the direction vector there, d. So if I take this formula for F, plug it into there, that distance is the magnitude of the displacement vector. That cancels, and what you're left with is that work is force dot displacement. Everybody see how that argument works? So the nice thing is that there's a really happy little punchline, and that is that we have to kind of scrap the old formula, the old high school formula of work equals force times distance over simplification. We have this did no consideration to the angle and to what extent is this in the direction of that. There's a whole story that you have to sort of asterisk and put on this. The correction here is simply to observe that force is not a scalar, force is a vector. Displacement is not a scalar, it's a vector. Both of these things have directions, in addition to the magnitudes that get talked about in high school, and the times in high school simply needs to be a dot product. The dot product accounts for all the direction nonsense automatically for us. So this is a wonderful result. By the way, we're going to be using that extensively when we get into chapters, into chapter 6, I'll say. Well, no, chapters 5 and 6. Turns out it's a big deal. Some of the types of integrals that we're going to be studying when we get to chapter 6 are heavily connected to computing work. All right. So there's an example here. I'm going to let you all read this example. It's just an explicit, given a force, given a displacement, and compute the work. It's just a dot product, and I'll let you guys read through that yourselves. Okay. So I'm going to move on now. We're done with section 1.3, bunch of exercises there for you. I'm going to move on now to cross products and determinants. This is that other matrix product that we talked about. Right? Remember, there's two different kinds of matrix products. Dot product is the one we've talked about previously. This is the other one. And turns out the cross products are closely related to something y'all might have seen in some limited extent before, namely determinants. It's curious, how many people have seen determinants at least a little bit at some point? Okay, all right. Well, you're going to probably see quite a bit more about determinants today than you've seen previously. And then, by the way, what I'm going to tell you today, tip of the iceberg. Turns out there's much more to say about determinants. If you take Math 216, you will see much more about determinants. There's a lot of surprisingly interesting, important facts about determinant that we just don't have time for in Math 212. It doesn't really directly connect to what we're doing. That also, not the whole story. There is more to say about determinants that doesn't get done in 216 either. Okay. There are lots of different ways to go through all of the facts that relate cross products and determinants. I've got a point of view on it, right? What you're going to see in the book here, my point of view on how to sort of most effectively introduce these ideas. It's not 100% complete. I'm going to state some of the facts without proof. So that's a disadvantage to the means I'm going to show you. But it has certain advantages. One of the big advantages is that the point of view I'm going to give you spends a lot of time the ideas that we end up going through focus on the geometric intuition for the objects we're going to be studying. I think that's a huge plus, and that's why I do it this way. So anyway, pros and cons. If you pick up a different textbook, or if you Google it, see what the Wikipedia page for cross product says. I don't know. It's liable to introduce the ideas in a different order, and there are many different orders to introduce these topics. Okay, so I'm going to start off by talking about an ordering concept, and here's the idea. Suppose I have a couple of vectors in R2. We're going to start off in R2 and work our way up to R3. And I have a couple of vectors. Well, here's the thing. I could write down those two vectors, v comma w, or w comma v. And I want to ask the question, how can I distinguish between these two orders? Now, when I say distinguish between them, I mean in a way that's geometrically relevant. It's geometrically natural, right? So I don't want to say alphabetically, this is an alphabetical order, that's in reverse alphabetical order. That's not geometrically interesting, right? So given a couple of vectors, putting an order on that pair of vectors, how would I describe what is it that is geometrically intrinsic to the order that I wrote those vectors down? And here's the idea. Let's suppose that this one is the first one I write down, so I'm going to write down v first. How would I describe, in relation to that, the direction that w points? And the way I'm going to do it is to say, well, look, that vector v defines a line. There are two sides to that line. Now, in this particular case, you might be tempted to say, well, there's a left side and a right side. But what if the line is like this? Now there's not a left and a right. Well, then there's a top and a bottom. Okay, right, fine. But then what if the line is like this? Now there's not a top and a bottom. So, what there always is, though, there's always a side to the clockwise, if you will, from where the vector points, and a side counterclockwise. Right? So that's how we're going to sort of get our foot in the door as to which direction w points. W is going to point into one or the other of the sides of that line, unless v and w are parallel, or one of the vectors is 0, or something annoying like that. Let's not worry about those cases. If w points into the side of that line that you would call the counterclockwise side, then we say that that ordering, where v is first and w is second, so that v comma w ordering, that's what we're going to call a counterclockwise orientation, because from the first vector getting to the second vector, you would go counterclockwise. Does that make sense to everybody? Any questions about this? About this ordering? So now there's a couple different things that I can say. There's likewise a clockwise ordering. That would just be if w is on the other side of the line. So I'm going to appeal to your geometric intuition. This is a nice little exercise you can think through for yourselves. But if you write down v comma w, and if that is a counterclockwise order, if you were to write them down in the other order, it will be a clockwise order. You just have to look at the picture and kind of think it through. Here's sort of an example. So v comma w, we just argued, with v first, it's counterclockwise to get to w. But if you were to put w first, it would be clockwise to get to v. Right? So v comma w and w comma v are always opposite orders. If one's clockwise, the other's counterclockwise. If the one's counterclockwise, the first one's clockwise, etc. Yes?
How do you decide that v defines the line? What if w?
Whichever one you write first. So keep in mind, what we're trying to do, we're not talking about the set that includes these two vectors. I'm talking about the ordering. So specifically, when I write v comma w, v is first and w is second. And whichever one is first is the one that defines the line. Whichever one is first is the one that you start rotating from.
Oh.
Yeah, exactly.
Well, then if it's w, v.
Then w is first.
Okay.
Whichever one is first. in the order. So you got, again, the big point here is we're not talking about two vectors. We're talking about an ordering, right? So one of them's got to be first, and that's the one that you start with. Absolutely. Okay, so this is kind of an interesting geometric fact that the two possible orderings are always opposite. One's clockwise, the other's counterclockwise, and vice versa. Here's another kind of cool fact, and that is that these two notions, the two different kinds of notions, are reflections of each other. Right? And this is an old fact, right? If there's a clock, you can see which direction the clock goes. If I had a mirror, and if you were looking at the clock in the mirror, it would look like the hands were going counterclockwise. Right? So clockwise and counterclockwise are reflections of each other. It's just another observation about this little system that we've created. Now, all of that being said, here's the big question. Here's the hard question. Suppose I want to do something kind of like this, but in 3 space with 3 vectors. Is there some geometrically kind of natural, relatable way of distinguishing the different orders that I might write those 3 vectors down? And it turns out that there's a great answer to this question. It's not obvious, surprisingly relatable once we get to it. By the way. So 3 vectors in R3, there they are, A, B, C. And again, thought of in that order. So A is first, B is second, C is third. What can I say? What is geometrically intrinsic to that ordering that I wrote down? Again, not alphabetical. I don't care about that. I'm talking about the geometric senses. So here's a way we do it. You take the first 2 vectors, A and B, and notice those 2 vectors define a plane. Now, there are some exceptions. What if A and B are parallel? Then, well, they don't really quite define a plane. One of the vectors is the 0 vector. There's several different annoying possibilities. We're going to ignore those. They come up sometimes. I just want to consider the generic cases where nothing weird happens. Okay. So the first 2 vectors, whichever of the first 2 in your ordering, draw them. That forms a plane. There's 2 sides to that plane. Top and bottom, front and back, left and right. All of these are kind of problematic points of view. The way I'm going to distinguish between the 2 sides of this plane is by using a right hand, a human right hand. And the idea is you put there's a certain gesture, you just have to know the rules on it's an arbitrary rule, okay? But the rule is right hand, your index finger parallel to your palm, your middle finger curled in the way that middle fingers want to curl, right? So no finger gymnastics, please, right? So curling the middle finger the way it wants to. If you put your index finger, again, parallel to your palm, in the direction of the first vector, again, this is an ordered list, one of them's first, put your finger index in the direction of the first vector. Arrange your hand in such a way that your middle finger, curling in the direction that middle fingers want to, points in the direction of the second vector. Look which side of the plane your thumb points to. It points to a well-defined side of the plane, right? If you follow the rules, first vector index finger, second vector middle finger, your thumb points to a well-defined side of the plane. And if the third vector points onto the same side of the plane that your thumb does, then we say that ordering, that's first, that's second, this is third, that ordering is what we call a right-hand ordering. Does that make sense to everybody? Okay. Now, there's the other possibility, of course. The other possibility would be, what if the third vector happened to point, that way? There's no law that says that it has to point on the side that my thumb does. If it points in that other direction, then it's not in right-hand order. Now, what should we call this other possibility that, half the time that third vector is going to point on the other side opposite from my thumb? Well, left hand, first finger in the direction of that first vector. Orient my hand now in such a way that my middle finger, curling the way middle fingers want to curl, points in the direction of my second vector. Now look at what I have to do with my left hand. Because it's my left hand, the way my hand is built, right, I have to sort of do this twist in order to get my middle finger to point in the direction of that second vector. Now look where my thumb's pointing. Pointing in the same side of the plane as the other vector. So right hand order and left hand order are always opposites of each other. That make sense?
Will it always be either left hand or right hand?
No, it'll always be the right hand or left hand, or something weird happened. So again, it's entirely possible, not generic, but it's, it will happen sometimes, that you'll be in neither. That the neither means that either one of the vectors is 0, two of the vectors are parallel, all three of the vectors are parallel to the same plane, something anomalous, a little bit anomalous and weird, yeah. But it is possible, right? Just like with two vectors, it's possible that the second vector might point exactly along that line, right? Or possibly even in the same direction as V, in which case then it's neither clockwise nor counterclockwise, yeah, totally. Okay, so this is what we mean by right-hand order. A couple of observations I want to make. First of all, these three orderings, ABC, BCA, CAB, always the same ordering. Now, I'm not going to prove this rigorously. I'm just going to make I'm going to try to sort of motivate it. This is a hand-waving proof. Sorry for the pun. But this is just so you have some geometric intuition for what's going on here. So I want to start with this possibility. So here's A, here's B, and here's C. All right? So A, B, C. Now you can see that as I have it set up here, A, B, C is a right-hand ordering, as evidenced by my right hand. Okay. Now let's consider BCA. That's A, that's B, that's C. So BCA is that's first, that's second, that's third. Also a right-hand ordering. All right, does everybody see that? So the idea, this in some sense, this little hand gesture here, is the motivation behind the idea that ABC and BCA are always in the same order. Right? And a very similar hand gestury proof will show that CAB also in the same order. Okay. So in fact, the way you can think about this is it's as if I'm leaving the A and the B there, and then I take this third vector C. Oh, I went in the wrong order, sorry. Boop. I leave the B and the C there, and I take the A and move it around to the other side to get BCA. And that's like a cycle, the listing of the vectors. The one that was first, move it around, make it last. And then again, you cycle these, leave the CA there, take the B, move it around over there, you get CAB. Right? All right, so those three orderings, always the same ordering. Interestingly, the other three possible orderings, also always the same. Same proof, they're just cycles of each other, right? Namely, if you start with ACB, take A and move it around to the end, that gives you CBA. So again, the same proof works, same motivation works. Okay. Also, not immediately obvious, something that you can persuade yourself with hand gestures, is that ABC and ACB always have opposite ordering. So these first three are always the same. The second three are always the same, but these two are always opposites. Right? So these three and these three are all different. And again, you can, hand gesture, persuade yourself that that's the case. Okay. I'll leave that as an exercise for y'all. Furthermore, the two geometric notions we're using are reflections of each other, just like with clockwise, counterclockwise. So right-hand order, left-hand order, mirror images of each other. If you take a right hand and look in the mirror, it looks like you're looking at that reflection person's left hand. All right. Okay, so a bunch of discussion about that. Now I'm going to talk about determinant. I think a lot of y'all have seen determinants. Here's the formula for a 2x2 determinant. So you have a 2x2 matrix there. AD minus BC. A lot of people like to do the little, make the little bow tie there. It's fine. So anyway, there's the definition of a 2x2 determinant. Make sure to know that. For a 3x3, the determinant formula is a little bit different. It's kind of a weird formula. How many people have seen this formula before? Show of hands. A few, not that many. Okay, all right. Side note, we commonly use bars to represent determinant. It's kind of a neat, convenient shorthand. The way we do this is we go across the top row. So going across the top row, you get the A1, the A2, the A3. For each one of these terms, here, let me do the A2 one. Cross out the row and the column that's in. Look at the remaining 4 entries. Assemble them into a little 2x2 matrix, and you multiply that determinant times A2. That's a weird little formula. So you go all the way across the top row following this little pattern, and then there's one other little twist, and that is there's some minus signs in here. Specifically, the first one is always plus. The second one you'll notice there is minus, and the third one is plus. So always plus, minus, plus. Going across the top row. Okay, it's a weird little formula. Again, much more to say about this in Math 216, those of you who I'll see next term. But that's all we're going to do with the formula for this term. Okay. All right, that being said, who cares? What does this mean? Why is this geometrically natural? What does this connect to? Did somebody just write down a weird formula almost seemingly randomly? Or does this mean something? Well, it turns out it means something. So I'm going to show you a picture of what this means. We're going to start off with a couple of vectors. Suppose I have a vector A and a vector B. These are two-dimensional vectors, right? 2 components, A1, A2, B1, B2. Let me draw a little picture up here. Okay, so first vector A, and second vector B. All right, now one thing I can do with that pair of vectors is I can take these vectors and make them the rows of a matrix. Now that's just an algebraic little move. I can take these numbers, I can make those the first row, I can take these numbers and make those the second row. Got a matrix. Here's another thing I could do. It's a little weird. But I could make the parallelogram that's sort of defined by these 2 vectors. I'm going to call that parallelogram by that notation there. I may have made this notation up, I'm not sure, but the 2 parallel lines to represent that this is a parallelogram, and then I indicate what the 2 vectors are that define the parallelogram right here. It's just a little shorthand notation representing the parallelogram defined by the vectors A and B, and otherwise it would have gone all the way across the page. So I love this little notation. I use it all the time. Be aware. Okay, so the weird thing is that this matrix, the matrix that you get by arranging the coordinates of the vectors as a matrix, versus the parallelogram that you get by looking at the geometric vectors, there's surprisingly a strong relationship between the matrix and the parallelogram. The algebraic sort of representation of what we're given versus the geometric representation. And here it is. It's pretty weird, really. But There's different possibilities as to whether the vectors are in counterclockwise order or clockwise order or neither. Those are the three possibilities. And the thing is, if they're in, I'm running out of colors. If they're in counterclockwise order, the determinant's always positive. It's weird. If they're in clockwise order, the determinant's negative. And if they're in neither order, so in other words, if they're parallel or one of them is 0 or something anomalous, the determinant's 0. So the ordering that I wrote the vectors down, keeping in mind which one's first, and therefore going in the first row, which one is second, therefore going in the second row. The ordering of the vectors correlates to the sign of the determinant. Weird. Here's the other weird fact. In all cases, the determinant relates to the area. Now, it's not equal to the area. Determinants can be negative, areas can't. But what is always true is that the absolute value of the determinant is always equal to the area. So the sign of the determinant tells you about the ordering of the vectors. The magnitude of the determinant tells you about the area of the parallelogram that they defined. That's super weird. It's very unexpected. It's an extremely unexpected relationship between algebra, this weird little arbitrarily defined determinant formula that's just a bunch of symbols that we wrote down, and these geometric ideas of ordering and area. I think that's an amazing little theorem. Okay, so curiosity, how many people have seen this theorem before? Show of hands, very few, none. Okay, all right. So that's a two-dimensional theorem. Note that everything here happens in R2, two-dimensional parallelogram there, etc. There is a three-dimensional version of this theorem. We're gonna do, oh, it starts there, okay. So suppose I have three vectors. A, B, oh gosh, orange, C. So three vectors. Those three vectors define a, not a parallelogram, but a parallelepiped, we call it. So A, B, C. So again, I can define, I can write down this this great big box, as it were, that they define. Right? There's a geometric object that's related, that's described by these three vectors. I can also write down the matrix described by those three vectors. Again, keeping the order in mind. So first vector, first row, second vector, second row, third vector, third row. And the weird thing is that it plays out exactly as it did in the two-dimensional case. Namely, there's three different possible orders: right hand, left hand, and neither. So three different. Now it's different what those three cases are, appropriate to the three dimensions, of course. But that being said, the determinant is either positive, negative, or 0. And in all cases, the magnitude of the determinant, oh, whoops, I had the wrong color. The magnitude of the determinant is always equal to, always equal to the volume. And again, you can't say the determinant equals the volume because the determinant's allowed to be negative. Volume is an intrinsically positive thing. So you don't say that the determinant equals the volume, but the absolute value of the determinant equals the volume. Just like in the two-dimensional case. This is super surprising, especially in the three-dimensional case. If you think about it, again, four-function arithmetic that goes into computing determinant. You're just adding and subtracting. You're not even dividing. It's three-function arithmetic. Right? And it's computing for you these really sort of awkward geometric things, such as how would I compute the volume of this parallelepiped. It's not even quite a box. It's a box where all the angles are weird, right? And the heights and the widths and stuff involve square roots, and it's very surprising. Okay. So I'm not going to prove this fact. I'm not going to prove the two-dimensional version either. It's tedious, and really there's a much better way to do it. The better way to do these arguments is to use more powerful tools than we have access to in Math 212. And I think it makes more sense to just wait until you guys see those tools as opposed to going to a lot of trouble to do something unnatural here. So I'm just going to cite these facts, and they'll be proved in future courses. Okay. All right. Okay. So a quick example. Here's a trio of vectors, and let's, what can we determine about these three vectors? Simply by computing the determinant. Well, the determinant, there it is -10. What does that tell me? Well, without having the slightest idea what the picture looks like, you'll note no picture, right? I see a minus sign, and that tells me that these three vectors are in left-hand order. And so if you were to, think it through, maybe try to draw a picture, try to draw the directions that these three vectors point, and think it through and realize that maybe I should look at it from this way. My left hand fits funny in the picture. You don't have to do any of that. Left-hand order. Negative. The parallelepiped that it makes has volume, 10, because that's the absolute value of this determinant. So again, you don't have to play a bunch of trig and compute square roots and have a nightmare of geometric challenge. Volume's 10. Okay, all of that having been set up, we're now ready to talk about the cross product. Keep in mind, we've talked about right-hand order, left-hand order. We've talked about determinant and how determinant relates both to order and to the geometric idea of volume. So now let's talk about the cross product. Here's the definition of the cross product. Given two vectors in R3, there's the formula. Now let me acknowledge that much like the formula I wrote down for the dot product, I seemingly have just pulled this out of nowhere, giving you no reason to believe that that's interesting. Then again, it worked out pretty well for the dot product, so maybe you're willing to believe that there might be something good a little bit down the road on this as well, and of course there is. But it's an arbitrarily written down formula. Now let me note here, dot products, we wrote down the formula for dot products in 3 dimensions, but you can do dot products in 2 dimensions. It's exactly the formula you would think. You can do dot products in 17 dimensions, whatever. The dot product is the same formula in all dimensions, very similar anyway. The cross product, as we are going to view it here as a binary operation, is peculiar to R3. You cannot take a cross product of 2 vectors in R2. It doesn't make any sense. There is no, you just can't, it doesn't work. And likewise in R17, if you have 2 vectors in R17, it just doesn't really make any sense. There is kind of an oddball, sort of analogous construction, but it's not a product, and it's kind of weird, and I don't want to talk about it, and we don't need to go into that. So as far as we're concerned in Math 212, R3 only. 3-dimensional vectors only. Okay. So given this formula, we can write down, we start computing the cross products of various vectors. Again, I've given you no reason to believe this is geometrically interesting yet. Let's start writing down geometric facts. And here is something that I made reference to recently. An example of an operation that we're going to be doing a lot with in this course, and it's not commutative. Now, it's so easy to just kind of take for granted, oh yeah, this symbol, that's the same symbol we used in elementary school, and 3 times 5 always equals 5 times 3, and that kind of thing. And you just kind of assume that, gosh, if you call it a product, doesn't it sort of have to be a commutative operation? And it doesn't. And this one isn't. All right? So make sure to be comfortable with this fact that it's simply not commutative. It's not hard to confirm that this, as written, is true. You've got a formula there for cross product. Just switch the order of the V and the W, and what you'll find is that everything goes negative. Okay. So that's a good exercise. I want to encourage everyone to do that. Persuade yourself where this minus sign comes from. It comes straight out of the formula, right? But, you know, confirm it for yourself. Okay. Now, I will say, even though it's not commutative, nevertheless, even though V cross W and W cross V aren't equal, they are kind of related there. I mean, that's a pretty interesting little coincidence, it would seem, that V cross W and W cross V, they're not just two random vectors. They're the negatives of each other, and that's also kind of cool. Right? So we say they're anti-commutative. All right. Here are some other facts that you can confirm for yourselves. This kind of, sort of looks like a sort of an associativity kind of thing, but you don't get all of that. And this is just a kind of a different construction. These are called triple products. So a dot product with a cross product. And triple products are preserved as long as you cycle the order that you write the vectors down. So U dot V cross W, if you take this W and move it over to the front, that's giving you W dot U cross V. Yes, those are equal. And again, if you take the V at the back here and move that around to the front, then you get V dot W cross U. Yeah, those are all the same. But only through cycling. There are three other expressions you can write down that look a lot like this, not the same. In fact, they're the negatives of these. And that's something you guys can prove for yourselves as well. Okay. One last cool fact, and again, you can, I think this is a homework exercise. Yeah, come to think of it, it is. The cross product is 0 if and only if the vectors are parallel. Or one of the vectors is the 0 vector, and that's kind of weird, but that happens sometimes. So other than when we're dealing with non-zero vectors, cross product is 0 if and only if the vectors are parallel. Now that kind of sort of dovetails pretty nicely with what we saw about dot products. Dot products are 0 if and only if the vectors are perpendicular. Cross products if they're parallel. Kind of neat. All right, all of these you can prove algebraically. I'm going to now sort of try to get into sort of, well, a little bit more algebra we have to lay down first, but we're going to, over the course of this section, find geometric points of view on all of these facts. So right now they're algebraic plug and chug. You're going to see a geometric angle on all of them. Okay. So I want to start off with a theorem here. If you take any two vectors, the cross product is always orthogonal to both of the input vectors. So V cross W is always orthogonal to V and orthogonal to W. That's a pretty neat fact if you really think about it, right? You give me two vectors, any two vectors, however they might happen to be oriented. Let's take these two. The cross product points that way, or at least a parallel to this line, right? That's pretty interesting. This is an easy proof. I'm going to leave the details for y'all. But if you want to show that the cross product is perpendicular to V, the way you show perpendicular, or let's say orthogonal, the way you show orthogonal is you compute the dot product and you just confirm that you get 0. Right? You want to show that the cross product is orthogonal to V, dot them, confirm you get 0. You've got formulas for all this stuff. Here's the formula for your cross product. We have a formula for dot product from earlier today. Just explicitly crank out this, and what you'll find is you get 6 terms, and they all cancel. It's kind of weird, but it works out. Okay. So I'm going to leave that as an exercise for you guys. Likewise for the other one, if you want to show that the cross product and W are orthogonal, the way you show orthogonal is you compute a dot product between the two vectors that you want to show are orthogonal. Again, you'll get 0 with this computation as well. Okay. All right. This formula for the cross product, you are going to need to be able to compute cross products given a couple of vectors. It's tempting to say that you should memorize that formula. I'm actually going to suggest that you do not memorize that formula as written right there, because it's confusing. It's easy to sort of twist it around and get it backwards, and it's so easy, for example, for the second component to write down V1W3 minus V3W1, and just to get these terms backwards. Super easy to mess that up. So again, I encourage you, do not memorize that formula. I'm going to show you a different version of this formula that's a lot more straightforward to memorize. It's going to take me a minute to sort of work my way up to it. So let's start with this assertion. The cross product that we wrote down on the previous page has 3 components. All I've done here is observe that the first component, now that's the first component, you'll notice, because that's what I'm multiplying by E1. E1 is a 1 with a bunch of zeros, etc. So that's the first component. And just notice that it is a little 2x2 determinant. V2W3 minus V3W2. You can see that right here. That's a little 2x2 determinant. That is. This second component, it's a little 2x2 determinant. Now, with the signs going kind of the wrong way, and this is a little bit annoying, but this determinant is V1W3 minus V3W1. I actually need the other. I need V3W1 minus V1W3. They're in the wrong order, so we have to put this little minus sign there. Slightly annoying, but anyway, that straightens that out. And then the third component, again, a little determinant. Okay. So having written that down, now this is just an observation. This is just noting that this is an alternative way to write that down. Doesn't that look a lot like a formula for a 3x3 determinant? It's kind of weird. It just happens to look like that. Something times a 2x2 determinant, 3 terms of that form, plus minus plus. Just looks exactly like that expression. Let me go forward now, back to here. Same structure, something times a 2x2 determinant, plus minus plus. So the tempting thing then is to rewrite that formula like this. Rewrite that expression as the determinant of this 3x3 matrix. Now, asterisk. Something has gone terribly wrong here. I have assembled into a matrix 9 objects, some of which are not numbers. Right? That E1, that's a vector. That's garbage. It doesn't make any. You can't make a matrix where the entries aren't numbers. That's the only matrices we know so far is matrices where the entries are numbers. Right? So this is a little sketchy. So I'm going to call this a symbolic determinant as a way of sort of acknowledging that, yeah, it's a little sketchy. It's not really technically quite. But the thing about it is the formula works out. Right? In other words, if you ignore the fact that that's not really a matrix and just compute the determinant anyway by the usual formula, you get this, which is the cross product. So this is a kind of a victimless crime kind of a deal. I mean, it's pretty handy. And what I like about this very much is that this is easy to memorize. Really easy to memorize. You don't have to remember where any signs are. Standard basis vectors along the top. First vector next. Second vector last. Just write down these entries, assemble this little fake matrix, and compute the determinant as you always would, following the determinant rules that you need to know anyway. And what's fantastic about this is it will always compute the cross product for you. Okay, so that is the formula that I have memorized. I have, in my entire life, never memorized this formula because I don't trust myself. I am quite sure that I would get it backwards and get a sign wrong at some point. Okay. Right. Okay. Last observation, and then we'll call it a day. But I want to squeeze in this one last little bit. suppose I wanted to know not just the cross product, but suppose I wanted to know what you get when you take a dot product of the cross product with some other vector. So this is that triple product construction that we saw on the previous page. How would I compute that? Well, the way you compute here we go. The way you compute a dot product is you take the one vector, right? You look at its components, and you multiply those components times the components of the second vector, and then you multiply and add. Right? So all I've done is take the components of the cross product, there they are, the components of U, and multiply and add. And weirdly, what you again get is an expression that looks just like a 3x3 determinant, and no asterisk here. That is full-on, actually, a 3x3 determinant of this actual 3x3 matrix, all of the entries of which are actual numbers. So there's nothing bogus about this, right? So, convenient fact then, triple products are determinants. Now, I wrote this a little bit differently here. I kind of like, instead of having to write U1, U2, U3, the whole point is that means that the top row is the U vector, and that's a little shorthand that I like to use to represent that the top row is the U vector. You just put the name of the vector, and I like to draw a little line there to make sure that it looks like it has the right shape. So really neat fact, then, the triple product construction that we saw on the previous page is a determinant. And this is our foot in the door. We're going to do this next time. We're going to use this fact to prove some amazing facts about cross products, and the way it's going to work is we're going to take advantage of this equation based on the fact that I already know a bunch about determinants. I know a bunch about determinants, right? It's facts about orders and facts about volumes. We know loads about determinants. I know loads about dot products, right? Components and various different things, angles, magnitudes. So knowing a lot about dot products, knowing a lot about determinants, we're going to be able to infer a lot of cool facts about cross products. So this is our algebraic foot in the door, and we'll pick up here next time. So see y'all later.